Hi, Pre-Calculus friends. We're in Chapter 11, Section 11.1. We're going to be talking about real exponents. So here's our notes and vocabulary. You are going to have to remember a couple things. Scientific notation, all right? And we're going to have to remember some of these rules with our exponential law. So let's remind ourselves of what scientific notation is. Scientific notation is a really great way for scientists and others to write and think about really large or really small numbers. So for instance, we were trying to write the numbers 523 millionths, no, 523 10 millionths, and this number 6 billion. And we wanted to write it in a more efficient way. What we could do is we usually put the first value in that has to be between 1 and 10. And so, or from 1 to 10. And so this would require us, I don't know why I'm explaining this like this is hard. This is going to require us to move the decimal place over 5 to 5.23. So that's the first part. But then we want to account for what we did. And that movement backwards, in a sense, or making this larger, needs to be accommodated for by dealing with the exponent of 10. So 1, 2, 3, 4, 5, that's 10 to the negative 5. That was not the best explanation. I'm explaining this to kids who actually know it. So that's great. But if you don't know it and you've never seen it before, I'm sorry, this is terrible. And then here we would do the same thing where we do 6, but 1, 2, 3, 4, 5, 6, 7, 8, 9. So this would be 10 to the ninth. So notice when it's a large number, you're going to have a positive exponent, a small number, a negative exponent, and the number to your 10, and the number you're always multiplying is somewhere between at 1 or greater, but definitely less than 10. Just a quick review. I hope that wasn't terrible. Okay, so this stuff, we have talked about this. You have seen this before in Algebra 1, probably Algebra 2. This is just the rules for dealing with exponential values. When the bases are the same, we can write it this way. So take a look at it. If you want to talk to me about it, personally, you're like, I need more help. Let's do that. We can discuss that definitely. Let's go ahead and look at this one. This might be new for us. So definition of b to the 1/nth is really going to be the nth root of b. That's how we would say that. And so we're so used to like the square root of 49 and everybody's like, that's 7. Really, what we don't tell you as terrible teachers is that there should be a 2 here. And so when we see 49, it's like 49 to the first power, but I'm taking 1/2, that 49 to the 1/2 power. That's where the 7 comes from. And so it doesn't just have to be 2. Usually we will write down as mathematicians the number that's other than 2. So we are comfortable with the convention that just means square root, even though we don't write the little 2 there. And now when we want to indicate that we're talking about, say, the third root, we'd write a little 3 there. And so we know that 2 times 2 times 2, or 3 2's multiply together to give me 8. So the third root of 8 is 2. Keep going with that. You guys get the idea. This guy brings in a little bit more drama to the mix. So we have this rational exponent of m over n. And what that means is the nth root, notice the denominator of that rational exponent will be the index number of our radical, the nth root of b to the m power, which is totally fine way of doing it. Or it might be more convenient to find the nth root of b and then raise it to the mth power. Both of these are equivalent, and it just depends on what's the easiest way for you to progress. All right, so with that, I think it's time for us to look at some problems or examples. So at the closest point, Mars and Earth are approximately this distance apart. Write it in standard form, and you would say gladly. So you've got the 7.5. You recognize that this 10 is to the 7th power, and so you're going to move it over 7 times. 1, 2. Let's try it again. 1, 2, 3, 4, 5, 6, 7. We're going to fill in the zeros there as we've moved our decimal place over 7 times. And then now we can look at this number and say that it is 75 million. So that's 75 million kilometers apart is the approximate distance from Mars to Earth as they're passing closest to each other. Okay, how many times farther is the distance Mars Pathfinder travels than the minimum distance between the Earth and Mars? So we're looking at the multiple value, and we also need to calculate this. I'm sure it's in your textbook, so I'm going to go and grab that. So now I've grabbed this information and now we're all set. So let's try again. How many times farther is the distance from Mars Pathfinder travel than the minimum distance between the Earth and Mars? And so if we're looking at that, we're going to be thinking about dividing. So we're going to take 4.013 times 10 to the 8th, and we're going to divide that by this distance here, by the minimum distance from Earth to Mars. And so when we do that, we can get, if we divide this, we use a little calculator, we can divide that pretty simply and we'll get like 0.54 about. And then when we divide this guy, we get times 10 to the 1, 8 minus 7, 1. And then therefore we see that the answer is approximately about 5.4 times the distance. All right, hopefully that made sense. Kilometers, I don't know. Yes, okay. So let's go ahead and look at this next one. Evaluate each expression. So these are kind of fun. It's us putting some of the laws together. This is the addition of the exponents when you have the same base. So at the top we can get 2 to the 12th power over 2 to the 5th. And then we know that we have to subtract the exponents when we're dividing two numbers with the same base, and we end up with 2 to the 7th. And of course we can calculate that value, and that's going to be 2 to the 5th is 32, 64, 128, I believe is right. Let's try this guy. We remember when we raise things to the negative, it really moves everything around. So what was once our numerator is our denominator. What was once our denominator is our numerator. So that calls us to take the reciprocal of the value inside. And so it's going to be 5 over 2 to the first power, or just 5 halves. Remember that there's a lot of different ways to answer these questions in terms of process. As long as you're using the laws correctly, you are golden. This next set, number 3, is going to ask us to raise each of these terms to the 5th power. So notice this 5 is going to affect everything inside. So this is s to the 2nd to the 5th is s to the 10th. Power to power, we multiply. T to the 3rd to the 5th is going to be t to the 15th. And that is as simple as we can write this one. Let's go ahead and look at this one over here. So I'm going to get rid of the parentheses by raising this already. And so I have x to the 3rd, y in the numerator, but in the denominator, I have x to the 12th. Power to power, multiply those powers. And then I'm going to sit down and take my time and do some canceling. I could look at this as x to the 3rd minus x to the 12th, which is going to give me x to the negative 9th times y. I'm not fond of negative exponents when I don't need to be, so I'm going to put it like that. You could also think about this as 3 x's at the top, 12 x's at the bottom. I don't feel like writing out all 12 of these, but sometimes it's just good to exercise your wrist. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hopefully I did that right. And that's all over this guy times y. So this is why this is why the subtraction works out, right? So we left with 9 x's in the denominator. All right, fun. Evaluate each expression. So what does this expression mean again? If you go back up to our work, we remember that denominator, our notes and vocabulary, our denominator is referred to as the index number. So that's going to be there. So what I'm going to do is see if there is a number in 125, or if 125 itself is a value that's being raised to the 3rd power. And fortunately for us it is, because I remembered that 5 to the 3rd power is 125. So I can successfully say that this is just 5. Over here, when I look at this, it's kind of like I can't take the square root of 14 and I can't take the square root of 7. Maybe if I looked at it differently, I could see something better. So when I see these radicals, I personally will multiply them together and say, okay, well, this is 14 times 7, which is going to be 98. So this is the square root of 98. And so now that I have that, I would break this down as I would any radical. I would see if there's a perfect square that is a factor of 98, and that does exist. That's 49. So 49 times 2 is what this breaks down to, and therefore we can take the square root of 49, and that's 7, but the square root of 2 we can't do, so it stays there. I think the textbook may have wanted you to rock like little rational exponents, but the reality is we're going to get to the same thing and put it at 1/2 and then kind of figure out what you could do. But, you know, same difference. I think it's all good. Here in example 5, we're going to simplify each of these expressions. So again, we've got the 1/4 on the outside, and we know that when we have an exponent on the outside, it affects each of the factors on the inside. So 81 to the 1/4 power, and then c to the 4th to the 1/4 times 1/4, or to the 1/4 power, is going to leave us with, well, 81 to the 1/4 power. I'm thinking that 3 to the 4th power is equal to 81. Therefore, this is 3. And 4 times 1/4 is just 1. So that's c to the 1st power, or just c. So that's how we'll get that. And over here, I can do this and write it as 9 times x to the 3rd and raise that to the 1/6 power. And so if I did that, I get 9 to the 1/6. I wanted it to be 1/2, but 9 to the 1/6 times x to the 1/2. Do you see that? 3 times 1/6 is 1/2. So times x to the 1/2. I put an x there. That should be 1/6. Okay. So there's a couple ways of thinking about this. The x to the 1/2 is what it is. It's the square root of x. That's totally fine. This guy is a little bit trickier because I can kind of reduce this. What if I looked at this as 9 to the 1/2 to the 1/3? Well, 9 to the 1/2 I can write as 3, so this would then be 3 to the 3rd, or the 3rd root of 3. So it gets a little tricky when we are asked to simplify. What is simple? What looks simpler? To me, this kind of looks simpler, right? Instead of writing all this other stuff out. However, we'll leave our final answer as the 3rd root of 3 times the square root of x, and we'll just leave it at that. Number 6 has us evaluating some fun things. So we remember that when we have this type of a rational exponent, we're going to refer to this as the index number 4, the denominator. 625 is in here. And now the question is, do I want to raise 625 to the 3rd power first, then take the 4th root of that? Or do I want to take the 4th root of 625 and raise it to the 3rd power? And I hear you screaming. You're like, please take the 4th root of 625, because we know that is just 5, right? Because 5 to the 4th power is 625. You guys remember that? Because 25 times 25 is 625. And that's 5 times 5. All right. Okay, so we're going to look at this. As we said, we're going to first take the 4th root of 625 to get 5. And now we're dealing with 5 to the 3rd power, which we remember from the last problem was 125. And finally down, well, I keep saying finally, but I think we have a bunch of examples here. So just keep some space available. So here we're going to use the rule where we know that we're going to subtract the exponents since the exponents are, since these values have the same base. And so we end up with 16 to the 2/4 power, or the 1/2 power, which we recognize as the square root of 16, which we recognize would be 4. All right, so number 7, we have to express this using rational exponents. I want you to hear ratio in the word rational exponents. So we're looking at ratios or fractions. So we want to use fractional exponents. So this isn't too bad. 64, we're taking the 3rd root of 64, so that's 64 to the 1/3, and that's going to be multiplied by s to the 9/3, and then t to the 15/3, which is 5. And so we've done that. I'm going to simplify it. The 3rd root of 64 is going to be 4, because 4 times 4 is 16, times another 4 is 64. So the 3rd root of 64 is 4. S to the 9/3 is really just going to be s to the 3rds. And t to the 15/3 is going to be t to the 5th power. Here we're to express this situation using radicals. Well, the 12 has no part in that, but we can write the x as the 3rd root of x squared, and I'll put the 2 in there, and this we can write as the square root of y. And we could write the 2nd square root of y, but the square root of y is what we would do here. Let me write that a little bit neater. So 12 times the 3rd root of x squared times the square root of y. But I didn't follow directions, did I? It says using a radical. So that doesn't make sense. Let's try again. So what we want to do is use one radical. And so that would mean that this just isn't underneath the radical. So I'm just going to leave this out for now. But if we look at this guy, these guys are kind of underneath two different radicals. So if I wanted to make them the same one radical, not the third root in the square root, but maybe just one radical, it would have to be the sixth root. So I'm going to rewrite this as 4 over 6. Notice I'm writing an equivalent fraction with what can be a common denominator, and this would be 3 over 6. You guys get how those fractions are equivalent, times 12. So now I can write this as 12 times the sixth root, that's a radical, follow directions, x to the fourth, y to the third. Thank you guys for being patient with me. Okay, so that's it for example 7. So here in example 8, we're going to simplify this as best we can. And we're going to come up with some information that you guys need to keep in mind. So here's the deal. I'm going to just tell you right off the bat, when you take the square root of a number, you know that that answer is always positive. It has to be positive. It has to be positive because the definition of the square root is the positive number, is a positive answer. So if I were to start off with a number like -3, right? And I were to square -3, I'd get 9. If I took the square root of 9, I do not get -3 back. I don't get that same value back. I get the positive version of -3 back. Why am I saying this? So when I take this, if I take the square root of c squared, if I take the square root of that, I don't get c. I actually get the absolute value of c because I'm putting these absolute values in here, these bars, because there's a possibility that c was negative in the first place. And if c were negative in the first place, I know I'm not actually getting c back. Let's hold this concept in the back of our mind as we work on this next example. So this example has us taking a look at each of these, taking the square root of each of these, and let's go ahead and write it as a rational exponent. So r to the 7th, s to the 25th, and then t to the 3rd. And I guess I can write this all as x. All of this to the 1/2. That makes sense. So then I've got r to the 7th to the 1/2 would be r to the 7 over 2. Then similarly, s would be to the 25 over 2. And then t would be to the 3rd over 2, right? And if I would break this down even further, I could look at this as r to the 6 over 2 times r to the 1 over 2. So what I'm doing is I'm making a distinction of what can become a whole number, and that's not underneath a radical when I'm done. And then similarly, this would be 24 over 2. That's s to the 24 over 2 times s to the 1 over 2. Remember, we add the exponents, so this is all equivalent. And then finally, t to the 2 over 2 times t to the 1 over 2. And so these guys that have fractional exponents still that will not resolve, that's the worst highlighter ever. These guys that have fractional exponents that will not resolve are going to be left underneath the radical. And so we have r, s, t, and that's the square root of rst. But what's going on the outside? Well, 6 divided by 2 is going to be r to the 3rd power. I got to think about this. If r in the first place were negative, r to the 3rd power would still be negative, and we cannot take the square root and get a negative answer. Thus, that has to be, absolute value has to be positive. We have to do absolute value of r cubed. Here, if s were to be negative, s to the 12th would be positive because it's an even number of numbers that we're multiplying, so it doesn't matter. So that's totally fine. If this were negative t, then t, the absolute value of t needs to be employed because this is just t to the 1st power. If t is negative, then it would still be negative. So this is how weird our answer can look. I know you probably don't like it, but we got to do that. All right, final example. Are you guys excited? I hope you are. So our final example is example 9, and we're going to be solving this situation, and it can be fun. So what we'll do is we will subtract 5 from both sides. We just want to isolate this x term. When we subtract 5 from both sides, we end up with 729 is equal to x to the 3/4 power. The thing is, I really want to know what x is. So I'm going to raise x to the 4/3 because then that's going to leave me with 1x. And what I do to one side, I'm going to do to the other. So x to the 3/4 to the 4/3 is going to just be x. And x to 729 to the 4/3 power, well, I know that I can take the third root of 729, and I could either raise 729 to the 4th power, then take the third root, or take the third root, then raise it to the 4th power. And you guys know what I'm going to do, because it will be a really big number. 729, you should be thinking about it. You're wondering, what is that? What do you raise to the... Okay, so if we take, I think it's 9. If we take 9 times 9 times 9, 9 times 9 is 81 times another 9, 729, yes. So if we take 9 and we raise it to the, if we take the cube root of 9, then we raise that to the 4th power, that's what x will equal. So basically x is equal to 729 times 9, which is 6,561. Okay, so that was a whole lot in a little bit of time. I hope it made sense. Let me know if there are any questions. I'll talk to you guys soon.